All right, this is problem number 48 from the AP Classroom Review for first semester. And I'll admit, looking at this problem, again, I saw it once before. I didn't think as much about it, but seeing this time, this is a little bit tricky. And this may be one when reading through on an AP test, I might say, all right, AP, if I don't have time, this one's yours. But let's go through some of the logic of this problem. It says the function h is differentiable. And for all values of x, meaning no matter what we plug in, h of x equals h of 2 minus x. Which of the following statements must be true? And when we say that phrase must be true, it means it's true everywhere. It doesn't matter what the x is. There's no conditions on it. So must is a pretty strong word, implying it will never not be true. Okay, I'm going to leave condition 1 alone to start with. And I'm going to work on this derivative bit. And so if we take the derivative of both of these, the derivative then, h prime of x, would need to equal h prime of 2 minus x times the chain of -1. So really we get h prime of x equals the opposite of h prime of 2 minus x. And that's what the derivative tells us. Okay, so now I'm going to use this idea and deal with the conditions that were given. H of 1, h of 0, and maybe h of 2 as well. So let's go through that. I'm going to start with that first condition, condition number 2. I guess it's not the first condition. So if we look at condition 2, it says h prime of 1 equals 0. Okay, well, let's substitute in 1. H prime of 2 minus 1. And if we simplify this, we get h prime of 1 equals negative h prime of 1. And if I solve for h prime of 1 by adding that h prime of 1 over, we would get 2h prime of 1s equals 0. And if I finish solving this, h prime of 1, regardless of what this function is going to be 0. So I am going to stick with 2. I'm going to make sure it has a 2 in it, option 2. So really my choices now are B, D, and E. I mean, I've narrowed it down. But let's see what else we can do with this. Let's see if we can continue to use that derivative idea. So let's look at condition 3 for a moment. And if we look at condition 3, 3 says that h prime of 0 equals h prime of 2, which has to be 1 everywhere. Let's see if we can work through that. H prime of 0 equals negative h prime of 2 minus 0. And we get h prime of 0 equals negative h prime of 2. So we're close to the condition, but I don't have a way to say with certainty. There's nothing I can do to add these. These are not like terms as they're written at the moment. I don't have any way with certainty to say that h prime of 0 equals h prime of 2, which equals 1. Also, let's look at a counterexample. And this is actually how we're going to go about proving number 1 as being incorrect also. But if we look at a counterexample, let's say my function h of x equals, I don't know, let's give it a constant. So maybe we call the constant, I don't know, h of x equals -1. Does that fit? It's differentiable. Its derivative is differentiable everywhere. Okay. And this would be true because if we had h of x equals -1, this is also equivalent to the fact that h of 2 minus x is -1. Regardless of what I plug in, h of 2 minus x will still be -1 if we set that to be true. So I'm going to let h of x be -1, which means h of 2 minus x also equals -1. So let's say, for example, we take the derivative. If I take the derivative here, h prime of x in this case would be 0. And h prime of 2 in this case, or sorry, h prime of, let's do that correctly, negative h prime of 2 minus x would also be 0. And so therefore, when I look at plugging in 0 for x, so if we let x be 0 in this case, this is condition 3 still, h prime of 0 is 0, and negative h prime of 2 is also 0, and so therefore condition 3 is gone. What that allows me to do is rule out D and E, thus leaving only B, meaning I didn't really have to focus on condition 1. Now, if I use that same idea that h of x was negative 1 in example 2, it would prove that it still works. Our goal was to show that h prime of 1 equals 0, and in that case it would in fact equal 0 if it was a constant function. Okay, so now let's look at condition 1 and why that one doesn't work, just to see. And I'm going to use the idea of the fact that we're going to let h of x equal negative 1. If we took the integral from 0 to 2 of the function negative 1 dx, and I integrate this, I'm going to get negative 1x evaluated from 0 to 2. When I do that, I'm going to get negative 2 minus 0, which equals negative 2, and that is not greater than 0. So condition 1 can be ruled out. So really, the best way to go about this one would be using a counterexample, because a counterexample, basically, if we can find one counterexample, we know the statement is false. And so since we were able to find one counterexample for both condition 1 and 3, same counterexample, we know they don't work. So this one was a little bit funky. Hopefully that helps.